Let's go ahead and get started today. Procedurally, I want to mention a couple things. Please try to be as neat as possible in your homework. The teaching staff has come to the conclusion we're spending an inordinate amount of time grading. A lot of that is just due to my style of doing things. As you've learned, I try to give feedback and partial credit and all sorts of helpful things on your homework. And it's kind of overwhelming us, just the amount of comments we do. So make your work as neat as possible so that we can award points as quickly as possible. And, hopefully you'll be happy with that. I guess in a similar vein, if you could get all of your work right, that would also make things easier to grade. But, I already know you're trying to do that. Alternatively, if you don't turn in anything, that's also easy to grade. But I'd much rather you do work that is, just 100% correct. Also procedurally, I graded, 1/4 of the exams. I'm working with the TAs to get the remainder of the exams graded, hopefully by Monday. You will be able to see your score after the curve and have all your feedback. Right now, things are, about what I expected for this exam. Like there's nothing, too out of the ordinary. And even grading just 1/4 of the exams, it looks like we are very much following a normal distribution so far. So I'm planning to use the normal distribution for the curve. No, I mean, I don't know if that's an is it centered at 50%? I don't know if it's centered at 50%. It might be centered slightly above 50%. But like the standard deviation is really low. Like not quite as low as it would be to be like a true, impulse, but like it's definitely a fairly tight standard deviation. Average might be like a 57% or something like that right now. If you remove all the zero scores. A curve. Yeah, we are expecting a curve, though one person managed to score extremely well. Like we have one score that is a few points shy of perfect, and after regrading it may be pretty much perfect. A would be one standard deviation above. Well, yeah, I mean, like I give you a numeric score. I don't give letter scores on the exams. I'd have to figure it out. Yeah. That's all I want to say on that. I won't know for sure what the exam looks like until Monday, right? Because today's Thursday. I'm definitely not going to know by tomorrow. All right, let's go ahead and get started with lecture proper. Still in cutoff, yes. We need 2 more people to arrive. Though I think it's getting harder and harder for us to reach our threshold voltage. Hopefully my lectures aren't that boring. That's always a fear I have as an educator. All right. So last time we talked about Laplace transform properties and started talking about the inverse Laplace transform. So, we talked about 4 properties, some of which are duals of each other. So one of which was this frequency derivative property, which is similar to the regular derivative property, time derivative property of integrals, of Laplace transforms. So after proof, we said that t times f of t Laplace transforms to negative d ds of f of s. And we can apply that to higher order derivatives. We can apply it to, polynomials, or at least the causal versions of polynomials that are off for all time and the turn on at time equals 0. they Laplace transform to n factorial over s to the n plus 1. Then we also have these, powers of exponentials, or powers of t times exponentials. So we get n factorial over quantity s plus a to the n plus 1. And we expect to see things like this show up because we've seen these sorts of responses show up in the output of our ODEs methods. We used ODE methods to solve circuits whenever we had repeated roots, or we had an input that matched the form of one of our homogeneous solution components. We would get a particular solution that involved these T multipliers. We looked at the time delay property. So if we delay a signal or by this, maybe with a u of t minus t naught here, then we also got a e to the negative s t naught times f of s. And by duality, if we move the e to the minus at to the other side, we got f to the at s plus a. So most of the time we use the time delay more often than the frequency shift, though the frequency shift was used to derive things like these exponential properties, or you can use it to derive the exponential properties and things like that. Also for complex roots, it will come in handy. But the time delays, for the unit impulse, the unit step, and the unit ramp, they all have these e to the minus st naught factor in front of 1 or 1 over s or 1 over s squared. Then if you have the Laplace transform of an integral, you get this. You get the Laplace transform divided by s of the original function, or I'll repeat that. If you take the Laplace transform, or the integral of a function and take its Laplace transform, you get the Laplace transform of the original function divided by s, plus the integral from negative infinity to 0 minus of the integral of the function itself over s. So what this can be interpreted as, remember when we took a derivative of a function, we got s times something minus the initial condition. Here, when we take an integral from minus infinity to t, we get the Laplace transform divided by s now, and then plus a step that handles all the values up to time equals 0. So it's like a step that injects it from there so that we deal with all the one-sided stuff, because this is a one-sided Laplace transform. We want the function to turn on at time equals 0 or afterwards. Yeah. Right now, yeah, you can find homework 4 up in the assignments page, but it's not up in the regular page because there was something we were double checking, and we wanted to make sure that when we put it up, there was no errors. I think it's okay, though. I'll ask about that. Obviously, we want to have homework 4 is still due on Monday, so I'll get that checked out today. Remember, homework 4 is 5 problems, but it's deceptive. Or wait a minute, homework 4 is 6 problems rather, but it's deceptive. I remember I got that wrong. All right. Enough with the procedural things. We're talking about Laplace transforms, everyone's favorite topic. So then we applied the Laplace transform to this circuit when we found its ODE, and then we used a delta function input and then try to find the inductor current. So we did this, and then we made some simplifications. So I guess, briefly walking people through it. The Laplace transform of this ODE is capital I sub n of s plus or equals L over R times S times IL of S minus IL of 0 minus, in parentheses. and then plus IL of S. Now we want to regroup things so that IL of S gets factored out because we want to solve for it, using algebra. And then, we want to have S L over R plus 1 minus L over R. And we don't like having any sort of coefficient besides 1 in front of S, so we'll factor out the L over R, and we'll get, 1 equals IL of S, L over R times S plus R over L, all minus 0. So we simplify algebraically for solve for IL of S. And then we match this with the Laplace transform pair, so we get R over L times e to the minus R over LT. Because 1 over S plus R over L, inverse Laplace transforms to e to the minus R over LT U of t. Then we redid this problem with IL of 0 minus not equal to 0. So we get I of S is equal to the same stuff, except now we have to deal with, this IL of 0 minus term. So we plug in I of S equals 1 because it's a delta function. So we get IL of S, L over R times S plus R over L minus L over R times IL of 0 minus. So we solve for IL of S. So we'll get 1 plus L over R IL 0 minus. We have to resolve the addition and subtraction first. Then we resolve all the multiplication with IL of S. So we say it's times R over L times 1 over S plus R over L. So you can simplify things through, and you'll get IL of t is equal to R over L plus IL of 0 minus. So its initial condition, e to the negative R over L t U of t. And already you can see sort of a beautiful thing that Laplace transforms does is rather than have to deal with initial conditions like separately or going back and finding the coefficients with the complete solution, the initial condition is baked into the Laplace transform solution process. So that allows us to save some steps in our brain when we're trying to figure out how to solve circuits. So then we change the input to this exponential input that matches that has a time constant that matches the natural time constant of the circuit. So we do this, and we notice we get, 2 S over R plus L terms, so that when we divide through, we get, an S over R plus L squared in the denominator when we solve for IL of S. However, you can regroup some things, and you'll get that, some of the terms, the S plus R over L cancels out, and then there's some terms where it will not cancel out. So we ended up with IL of S is equal to IL 0 minus over S plus R over L plus R over L I1 over S plus R over L quantity squared. So we got a normal exponential decay, and then we also got this other term that has an t times the exponential decay. So all is right with the world. This matches what we learned with ODE circuits. I hope you got sick of seeing the parallel RL circuit because it's going to come up again and again and again, along with the RC circuit and so on and so forth. Any questions about what we talked about with Laplace transform properties and how we could apply it to circuits? Step 2 of which slide? Slide 30. Okay, so generate the ODE for this circuit. Hopefully we know how to use KCL by now and say, okay, IN is equal to IR plus IL of t. And then, we can rewrite IR as 1 over R times VL, where VL of t is the voltage across the inductor, which is shared by the resistor. And then VL is equal to L DIL dt. So we get IN of t is equal to L over R DIL dt plus IL of t. Next, we take the Laplace transform of this. So we get in of s equals L over R times the Laplace transform of derivative is s times the Laplace transform of the function minus the initial condition, and then plus IL of s. So we would end up with something that looks like this right here. But now IL of 0 minus is non-zero. So we'll just move the L over R IL of 0 minus to the right-hand side, and we'll regroup the IL of S terms. So we'll get IL of S plus L over R plus 1 minus L over R IL of 0 minus. So if you're wondering where the IL of 0 minus comes from, it comes from the definition of the derivative property of the Laplace transform. Cool, glad you get it. So we learned about the most important property of the Laplace transform yesterday, and that was the convolution property. So lo and behold, the convolution of two signals is equal to the multiplication of their Laplace transforms. Convolution in time is equivalent to multiplication in frequency. This is a huge result because we solved, y of t is equal to x of t convolved with h of t. So we'll get, as we saw all the way back on slide 8, y of s is equal to x of s times h of s. So we can find the output to an LTI system by multiplication now in algebra rather than having to do a convolution integral. So this is nice. This is wonderful. And we jump forward a bunch of slides. You will see this concept come up again and again and again. This is the heart of what allows us to basically, this is the heart of what allows us to basically say the Laplace transform can do everything that we learned in lecture set 3, but, easier. I won't say that you can ignore what you learned in lecture set 3 because it's going to show up on the exam, but this is totally, what allows the Laplace transform to be so useful to us. So we talked about time and frequency duality, including those dual properties, and including, you can take the convolution property and look at its dual, the multiplication property, A of t times B of t, Laplace transforms to Laplace transform of A convolved with the Laplace transform of B. So the duality, where manipulation in either domain produces equivalent changes to the other domain, allows us to solve more problems. I claim it's nearly twice as many, but most of electrical engineering has duality. Duality between electricity and magnetism, duality between inductors and capacitors, duality between voltage and current, duality between any number of concepts. So, resistance and conductance. So, we're very used to duality. It allows you to do twice as much with half as much knowledge. Don't check my math on that claim. I mean, right now we still need lecture set 2. Up until later today, we still need lecture set 2 in order to derive the ODE. Once we have the ODE, we Laplace transform it and then don't deal with it. So we don't need like the particular solution and complete solution methods, but we still need the ability to derive an ODE. Once we talk about impedance admittance, we don't even have to derive the ODE first. Riyadh. So then we talked about the inverse Laplace transform, and it's denoted with the calligraphic L to the -1. And we learned that it has this horrendous contour integral that requires complex analysis in order to do reliably every time. Completion of the residuals at the poles, nonsense like that. Rather than deal with this sort of definition, we're just going to pattern match with the Laplace transform table that you'll be given on exams and for homework. So every function we have is going to we're going to deal with that corresponds to a stable system is going to have something that's of this rational function form, where we have a polynomial of degree m divided by a polynomial of degree n, where m is less than or equal to n. And it's going to be factorable into poles. Sometimes you need the complex numbers to factor them, but you can always factor a polynomial into poles by the fundamental theorem of algebra. And we can turn this product of factors into, in the denominator, into a sum of denominators with individual factors. So we're going to look at 4 possible cases for what the roots are. We looked a little bit at the distinct real root case, where we dealt with these functions: Laplace, inverse Laplace transform of a constant, inverse Laplace transform of a linear term reciprocated, and then we learned how to get coefficients k and ai. So your homework was to look up the Heaviside cover-up method and see if you can use that to get faster at solving these types of problems. So by the rational root theorem, we were able to figure out that the poles of this cubic polynomial were were -1, -3, and -7. That's where the poles are. So the factors are s+1, s+3, and s+7. We can separate them so that it's a sum of individual factors in the denominator with unknown coefficients in the numerator. So we multiply through to clear the fractions if we want to do this the formal way. And then we start plugging in values that will make each of these terms go to 0. In reality, we just need to plug in 3 different terms. It can be any values of s because the coefficients have to hold for all values. However, why make our life harder when we can choose easy values that allow us to solve for terms outright? So we notice if we plug in -1, the last 2 terms go away on the right-hand side, leaving us with just something that we can solve for a1. If we plug in -3, the first and third terms go away, leaving us with the second term. If we plug in -7, the first 2 terms go away, leaving us with the third term. So you have to remember how to, take the squares of, negative numbers and stuff like that, and then, do a lot of multiplication and addition, subtraction, but it's all arithmetic. And you can get, by plugging in -1, a1, by plugging in -3, a2, and by plugging in -7, a3. And then you go back to our original form where we said f of s is equal to this, expression. And then we get, f of s is equal to -1/4, 1 over s+1. Well, that term becomes -1/4 e to the minus t u of t. This term becomes 7/9, or no, you gotta be kidding me. I screwed it up. It's 7. It's supposed to be an 8 in the denominator there. 8, 7/8. 1 over s+3 becomes 7/8 e to the -3 t u of t. And then 9/24, 1 over s+7 becomes 9/24 e to the -7 t u of t. I factor out the u of t because law of the conservation of ink. We can use the rational root theorems to detect division. We extract the coefficients, inverse Laplace transforms. Yep, nothing too out of the ordinary here. And then if there was, equivalent degrees in the numerator and denominator, we would have to include a k in our partial fraction expansion, but we can always choose s equals infinity or some other value to solve for the k. Aubrey, a tenured ECE professor. Oh boy, like 15 years. I think you're being both optimistic and pessimistic at the same time with that time frame. Also, okay, I'll let you in on a secret. The first semester you teach a course, no matter how much you try to prepare, it's always rough. So this is my first time teaching ECE 2002. It's rough, but man, I'm sorry for the errors. I really am, but it's just you don't notice these things until you're literally in front of people. I'll remember you. You've been a pretty good group. I like this class a lot. I don't say that about every class I teach. Anyway, we're on to new content now. So slide 38. So now what happens if we have repeated real roots? This is case 2. So that means in our factored form, we have some pi is equal to pj for some I not equal to j. So that means, for example, like p3 and p4 are the same pole. Well, we need to know the following inverse Laplace transforms. The inverse Laplace transform of a constant becomes k delta t. Inverse Laplace transform of aj over s plus a becomes aj e to the negative at times u of t. A sub j over s becomes aj u of t. And the linear term to any negative power. So if we have aj times n factorial over s plus a to n plus 1, we get aj t to the n e to the minus at u of t. Most of the time, we just deal with n equals 2. Actually, we just deal with n equals 1 most of the time. Whoops. So yeah, if we deal with n equals 1, we get aj over s plus a squared. Laplace transforms to aj times t times e to the negative at. But we can just generalize it to any power of n. And, as electrical engineers, which are, indistinguishable from mathematicians at a distance, we like to generalize things. So when we have these repeated real roots, we have to use convenient values of s to find the lower powers of repeated roots. We'll see that there's a problem when we do our partial fraction expansion, or we can't just solve for things outright. Hey, threshold voltage bet. AJ, yep, I've been talking about you this whole time. We named the constant after you. Like, most people go their whole lives without a constant being named after them. But like, all throughout this lecture set, you have a bunch of constants named after you. Good job, AJ. I'm trying to think. Does anyone else have a 2-letter name that gets, or 2-letter initialism that they use? Like, you probably have a constant named after you. So here we go. Here we have f of s is equal to s squared plus 6s plus 2 over s cubed plus 4s plus 5s plus 2. Well, rational root theorem tells us that the only possible rational roots would be plus or minus 1 or plus or minus 2. And in fact, we get s plus 1 quantity squared times s plus 2. So we would get a1 over s plus 1 plus a2 over s plus 1 squared plus a3 over s plus 2. Notice you have to include all the lower powers as well as each successive power of a repeated root. So you have to have an a1 s plus 1 and an a2 over s plus 1 quantity squared. Otherwise, you're not going to have the right form, and all your math will be awry, and you'll be very sad that you can't get the right answer. But, this a3 over s plus 2, when we multiply through, we get s squared plus 6s plus 2 equals quantity a1 s plus 1 s plus 2 plus a2 s plus 2 plus a3 s plus 1 quantity squared. Because, you get the relevant cancellation of the factors when you multiply through. Solving for this last one, well, everything has a s plus 2 in common except for the last term. So if we plug in -2, it's just like solving for the distinct real root case. So you'll get 2 squared minus 6 times 2 plus 2 all over. Well, -2 plus 1 is -1 squared. So you work this out, you get -6. Well, you go back here and you're like, okay, well, if we plug in -1, the first term and the third term disappear. So if we plug in -1, we get 1 minus 6 plus 2 over 1 equals -3. So we could solve for the highest power, or the coefficient to the term with the highest power of a factor in the denominator. but we couldn't solve for the lowest one. Uh-oh. How are we going to possibly do this? We have to resort to some sort of system of linear equations. If there were multiple of them, technically this is a system of one equation, but we're going to plug in s equals 0 because s equals 0 is a very convenient value. So we're going to get a1 over s plus 1, s plus 2, plus a2, s plus 2, plus a3, s plus 1 quantity squared. Plug in 0, all these values. Well, you get, what's in front of a1 is 1 and 2. And then you're going to get 0 plus 0 plus 2 minus a2 times 2 minus a3 times 1 squared, where we have values for a2 and a3 already. So when you plug in the numbers, you'll get 7 because you'll get, 2 minus negative 3 times 2 minus negative 6 times 1. And if my math was good when I made these slides, that equals 7 when you divide it by 2. So now we have each of these coefficients. So we say f of s is equal to this, but we plug in the coefficients. So we get 7 over s plus 1 plus negative 3 over s plus 1 quantity squared plus negative 6 over s plus 2. Well, we know the Laplace transform of this first one is 7 e to the negative t u of t. This last one is negative 6 e to the minus 2t u of t. And this one is going to be negative 3 times t times e to the negative t u of t because of the power involved here. That goes back to what we said here when you plug in n equals 1. Now, we didn't have to choose s equals 0. You could choose s equals 100 or negative 99, but that would be silly and be very hard on you. So chose a convenient value like s equals 0 to solve for a1. So there needs to be n equations and n lower order coefficients to solve them. Like I said, we did one equation in one lower order coefficient to solve it. And this solution would match what we know about ODE solutions. Like, yeah, we can see how this is the equivalent solution of some ODE. What questions do we have? So the Heaviside method, as far as what most people would consider the Heaviside method, only works with the highest order root and the highest order pole. So if there's s plus 1 and s plus 1 squared, it would only get you s plus 1 squared. And there was also s plus 2, it would get you s plus 2 because s plus 2 was the highest power of that pole. It doesn't get you the intermediate one. Now, I'm sure someone's developed some trick that would make it go faster, but I don't think it's called the Heaviside cover-up method. So so my philosophy is, as soon as I see that there are repeated roots, I don't even bother with Heaviside because I know I'm going to have to write out this equation anyway, where I clear the denominators and solve for terms and choose convenient values. Since I'm going to do it once, I might as well just do it for the whole problem. Good question, Aubrey. So let's move on to the next case. So what if we have conjugate imaginary roots? So something of the form s squared plus, some magnitude of pi squared in the denominator. So we'll have the constant, the linear term with aj, e to the negative at. And then we have a quadratic term without a linear term reciprocated. So if we have ai s over s squared plus omega naught squared, we're going to get ai cosine of omega naught t u of t when we take the inverse Laplace transform. Similarly, when we get aj times omega naught, which is just a constant, over s squared plus omega naught squared, we're going to get aj times sine of omega naught t u of t in inverse Laplace transformed. And unfortunately, whenever we see terms like this, we're going to need to take an affine term affine means basically, mx plus b type form, where you have, something times the variable plus a constant. So it's linear plus a constant of the term corresponding to conjugate roots. I'll show you what I mean. Say we have f of s is equal to 2s plus 1 over s cubed plus s squared plus 9s plus 9. You can factor out s plus 1 out of everything. And you get s plus 1, s squared plus 9. So when we write its partial fraction decomposition, we get a1 over s plus 1 plus a2 times s plus a3 all over s squared plus 9. Notice when we do this, we have to have a linear term in the numerator. We always want the term to be 1 power less than the power represented here, unless it's like this case where it's the whole power squared, and that way you can just get by with just the constant term. The rules for partial fraction expansion are, they're long. There's no other way to say it. Is you just have to know these rules and get comfortable with all these cases. There's really just an aspect of memorization to this. There's no way around it. So we clear the denominators. We get 2s plus 1 equals a1 s squared plus 9 plus quantity a2s plus a3 close quantity times quantity s plus 1. Well, we can get rid of the last term, the last, basically two terms completely by multiplying by, or evaluating s equals -1. So we'll get 2 times -1 plus 1 over -1 squared plus 9, or -1/10. Now notice, we can actually make this middle term disappear by choosing s equals 0. So if we choose s equals 0, we get, 1 on the left-hand side minus a1 times 9 divided by the 1 here equals a3. So that's equal to 19/10. And unfortunately, there really isn't a good thing we can do to solve for a2 by itself. Nothing really makes the a2 term appear alone. So we just choose a convenient value. We already chose -1 and 0. I recommend choosing 1. If you don't like 1, maybe 2 or -2. Probably don't want to choose 55 or some weird number like that. Choose a nice small number. It doesn't even have to be a real number. You can choose j or -2j or something like that if you really needed to. I like to work with real numbers whenever I can, though. I'm sure many of you feel similarly. So we plug in 1 on both sides. So we're going to get, we're going to get 2 plus 1 minus a1 times 1 plus 9 divided by 2. And then after that, we have to subtract off the a3. And we're left with a2. So this is just an algebraic rearrangement of the previous evaluation. It just takes a little bit of, looking around to see where it is. So we have the 2s plus 1 on the left-hand side, which is going to be in parentheses. We have to resolve this addition. Then we have to resolve the multiplication by this factor. And then we have a parenthetical grouping we have to resolve. So there's some addition in the parenthetical grouping to resolve. So that's how we get, this bottom line. Solve it out, and we get positive 1/10. So here we go. We chose two convenient values. S0, I actually chose s equals 1 instead of s equals 2. Right, that's another error to fix. So we got f of s is equal to -1/10 1 over s plus 1 plus 1/10 s over s squared plus 9 plus 19/10 1 over s squared plus 9, where we broke up this term because the addition is in the numerator. We can just break it up into the first bit over the denominator plus the second bit over the denominator. We're good to go for the first two terms. However, the last term needs some massaging because, s over s squared plus 9 matches our form right here. But for this other term, we need omega naught over omega s squared plus omega naught squared. So we need to multiply top and bottom by 3. So top side by 3, bottom side by 3, so we don't change the equality. And sure enough, 9 is just 3 squared. So that's why we chose 3 for top and bottom. And then we'll get negative 1/10 e to the negative t plus 1/10 cosine of 3t plus 19/30 sine of 3t all times u of t. So whenever you see a sine-like term where, it's like some constant over, some s squared plus a constant, get used to having to do a little bit of massaging to get it into the right form for the inverse Laplace transform. Questions? Yeah. If you choose those numbers, I will be very angry after I said choose convenient values. But like this, you can choose complicated values. You just have to get it right. If you choose bad values and get it wrong, I do not want to sit through your work and try to find exactly where you did a multiplication error or something like that. So you've been warned. I'll be less generous with points if you're choosing values that make me think too hard. All right, we have the last case for our form for the rational functions after partial fraction expansion. So we can have complex conjugate roots in the denominator. So s squared plus as plus b. So again, Laplace transform constant, linear term reciprocated. Now we have a quadratic form with a linear term. So if we have ai times quantity s plus a over quantity s plus a squared plus omega naught squared, that inverse Laplace transforms to ai e to the negative at cosine omega naught t u of t. This is the, the exponentially damped, sinusoid. And the counterpart is we have aj times omega naught all over quantity s plus a close quantity squared plus omega naught squared. Inverse Laplace transforms to aj e to the negative at sine of omega naught t u of t, where it's the other counterpart of the exponentially damped sinusoid. So two coefficients in an affine form in the numerator corresponding to conjugate roots. So rather than work out the example completely from scratch, where we have to factor the numerator denominator, oh, look, someone did it for us. Someone found the coefficients for us. So we can spend a little bit less time on this example. You kind of know where this is going. So we lost 6 over s plus 1 plus 5s plus 6 over s squared plus 4s plus 13. Okay, the first term is good. So 6 over s plus 1 plus this is going to be equal to the 6 over s plus 1 term. Perfect. Now we need to get something that we factor the denominator. The way we do that is by completing the square. So remember, to complete the square, s squared plus 4s, remember we need to have b over 2 quantity squared. So 4 over 2 is 2 quantity squared. So we need a 4 from the 13. So we borrow 4 from the 13 and we're left with a 9. So we get s plus 2 quantity squared plus 9. Hopefully you all remember completing the square. So this is the term we need to match for our cosine term. So we need to do a little bit of massaging of the cosine term even. So we can factor out 5s plus 2 from here. So the 5, just because it's the coefficient. Then s plus 2, that gives us 10. We need to subtract 4 to get back to where we were. So we get 6s plus 1 plus 5 times quantity s plus 2 over s plus 2 quantity squared plus 3 squared. And then we'll have a minus 4. But we need to have omega naught and the numerator of its term. So we'll make it multiply by 3, divide by 3. So we'll make it minus 4 thirds times 3 over s plus 2 quantity squared plus 3 squared. Inverse Laplace transform that to get 6 e to the minus t plus 5 e to the minus 2t times cosine of 3t minus 4/3 e to the minus 2t times sine of 3t u of t. We complete the square. We use the frequency shift property to get, this, nice little form I gave you on the slides. So that's the use of the frequency shift property. We massage the sine-like terms to get the right numerator for the inverse Laplace transform. Any questions about how we did this? What do you mean by doing two transforms at once?
Can you hear me?
I can hear you.
All right. I mean, like, so that last term you have like 3 over s plus 2 squared plus 3 squared. Is that like a form that's on the Laplace transform table, or?
It should be. It'll be on your Laplace transform table.
Okay.
It's not on every Laplace transform table. You can, like I said, derive it from the normal one for cosine and sine. You just have to use the frequency shift property.
Okay.
Or remember, if you multiply by e to the negative at in time, that's the same thing as replacing every s in the Laplace world with s plus a.
Okay. Are we gonna have to do 2 at once eventually? Because I remember in Diffie-Q, that was a thing sometimes.
What do you mean by 2 at once? I still don't understand what you mean by that.
Like, we would have to use 2 Laplace transforms on the same term sometimes.
Transforms on the same. I don't think you would have to do that, because like if you have a good Laplace transform table and you know your Laplace transform properties, you're applying a property to an existing transform. But you're not
Okay.
really doing 2 Laplace transforms. You're not like Laplace transforming and then Laplace transforming again. You wouldn't want to do that.
Yeah, I know that. I meant like there were sometimes when you had to like look at 2 different transforms on the table to like figure out the one that you actually needed.
Sometimes you'll have to look at a transform in a property. So
Okay. Thank you.
I can't guarantee that your Laplace transform table is going to be perfectly, adequate for every problem you'll ever be asked, but I'll try to give you a fairly complete one. Okay. So I want to close off today with some examples. So we'll find the output waveform for the system with input waveform x of t is equal to x sub a e to the bxt u of t, and impulse response h of t is equal to h sub a e to the bht u of t, where b of x is not equal to b of h. So we mentioned this, that, if this was an LTI system, it would be a convolution of these 2 waveforms, or in Laplace world, it's just a multiplication of the 2 waveforms, or 2 spectra, I should say. So Laplace transform x of s is equal to x of a over s minus bx. To match this form, we have to use a minus sign. H of s is equal to h of a over s minus b sub h. We multiply to get y of s, so we get x of a times h of a over s plus s minus bx times s minus bh. Okay, this form looks familiar. So we have a rational function where we have a constant in top, and then we have a polynomial in the bottom. We can do partial fraction expansion to get a1 over s minus bx plus a2 over s minus bh. What is a1? Well, I'm going to, quickly cover up the x term and then plug in s is equal to what I covered up, which is the bx. So we'll get xa times ha over bx minus bh. And then for the cover up method, we're going to cover up the s minus bh term. What makes it 0? Plugging in s is equal to bh. So we'll get XA times HA over S or over BH minus BX. Well, one term is just the negative of the other. So I'll just write it as y of t is equal to XA H of A over BX minus BH times quantity e to the BXT minus e to the BHT U of t. And call it good. 4 steps to do an entire LTI system response, which would have been about 7 steps with convolution. Now let's make things a little bit more complicated. Same system, same waveforms, but now B of X is equal to B of H. So I'll write X of S is equal to S XA over S minus BH, where B of X is equal to BH, so I can do that. So when we multiply, we'll get X over A, H of A over S minus BH quantity squared. But hey, this is already in the form of one of our terms where we have 1 over or a constant times S plus A to the second power. So we can take the inverse Laplace transform directly. We'll get y of t is equal to x sub a h sub a times t e to the bht u of t. Really fast. 3 steps to do an entire LTI system. And then we'll look at this. So we'll have an output waveform for the system with input waveform x of t is equal to xu of t minus t naught. Impulse response is equal to h sub a sine of omega naught t u of t. So we're inputting a step function, and the impulse response, for some reason, is just a sine wave. So this is a delayed step. So we'll need a factor of e to the negative t naught s, and then times x over s, because it's a step. And then this is h sub a times omega naught over s squared plus omega naught squared. We multiply results. We get x times h sub a omega naught e to the negative t naught s over s times quantity s squared plus omega naught squared. So we'll do Laplace partial fraction expansion on everything but the e to the negative t naught s term. That's kind of separate. It can tag along later. So why not, neglecting that term is equal to a1 over s plus a2s plus a3 over s squared plus omega naught squared. So we solve for s equals 0. We get a1 is equal to x sub a h sub a over omega naught. And then, unfortunately, the convenient 0 value we normally use for a2 is already been taken. So we have to use 2 other values. I use +1 and -1 to get the other coefficients. So we set up a system of linear equations. And we get a2 is equal to negative x sub a h sub a over omega naught, and a3 is equal to 0 in this case. We can solve this one just by adding the 2 equations together, by the combination method for solving linear equations. So we perform the inverse Laplace transform, and we'll get y of t is equal to x sub a h sub a over omega naught times quantity 1 minus cosine of omega naught times quantity t minus t naught, closed quantities, u of t minus t naught. Why is there a t minus t naught in the argument of cosine? Well, that's because we still have this e to the negative t naught s floating around, and it time shifts every single thing when we take the inverse Laplace transform. And that makes sense. You don't want the cosine to appear in anticipation of the input waveform. It has to wait until the input waveform appears before we can get an output waveform. What questions do we have? there aren't any questions, let's go ahead and call class here today. We'll start next time with discussion of impedance and admittance, where we'll learn that we no longer need to even write the OD first to solve our circuits. We will just be able to write them using our good old circuit rules that we remember from ECE 20001. So big appreciation. I appreciate you all too. Goodbye. You're welcome, everyone. You're welcome. Are you able to do all your homework? Oh, I'm sharing my screen. I should stop sharing my screen. No, you cannot do 4, 5, and 6. We unfortunately have to wait until tomorrow for the last 3 questions. I'll see if we might have to change the homework. If we don't get to everything, I will remove questions from the homework or postpone it. Goodbye. You're welcome.